Varant, he spent 10 years building data infrastructure for AI and ML at Airbnb and Palantir. We won't hold it Palantir against you. Um, and during that time, he became one of the original authors of Chronon and the recently open source feature store. And he's currently co-founder of Zipline AI, who are building an enterprise platform around the project. Go for it, Varant.
Yeah, thanks so much. Thanks, Jim. Yeah, so I think, by now, a lot of folks in the community have probably heard something or another about Chronon, maybe one of the prior talks today. But I wanted to start with a little bit of background and kind of tell some of the story behind it. I think it's sort of interesting for folks that have kind of gone through similar journeys. So as Jim mentioned, we started off at Airbnb. And actually, when I started working at Airbnb, there was no ML infrastructure team. There was just this data infrastructure team that I was on. And we would work sort of embedded with various customer teams across the company. And at the time, I was focused on teams that were trying to do production AI or production ML. Um, and one of the first teams that we came across that had a big pain point was the payments trust team. So payments, Airbnb is a travel company, but it's also very much a payments company in that it moves a huge amount of money across bank accounts, across borders. And as a result, it has a lot of the same payments fraud challenges that other payments companies have, more traditional payments companies. And so the team was struggling with the fact that payment fraudsters are quite adaptive and iterative and quite sophisticated in general. And so what this team wanted to be able to do was iterate just as quickly. So iterate on fraud models, detect new patterns of behavior, respond by updating the models, and so on and so forth. And the bottleneck, as we kind of dug into their pain point, why they couldn't do this, the bottleneck was really in the feature engineering side of things. And then there's other trust and fraud use cases like login fraud, bad actor detection, those kinds of things. And so basically the outcome that we had after a couple of months of working with them and building out this infrastructure was able to take their iteration loop from months to days. And then that kind of got some other teams' attention. And so the search team came to us next, right? And they were like, well, look, we want to be able to iterate as well on our search personalization models. So recommending better items to users, both here on the homepage as well as in search results. And similarly, the bottleneck for them was in feature engineering, data engineering for our features basically was where the bottleneck was. But what's interesting about them was that there's a couple new requirements. Latency budget extremely tight and scale for training data generation extremely high. Airbnb, every time you click that map and you drag it, that's a new search event that populates thousands, hundreds or thousands of listings. And all of that is data that's being generated and needs to be fed into training and inference and all that stuff. So we spent a little bit more time with them to kind of expand the engine to be able to work at that scale and with those budgets. But what was interesting was that by the time we did that, and we were working kind of well for their scale, and we landed a similar impact for the search relevance team as we did for the trust team, now we were kind of ready for any use case across the company. So people started kind of coming on their own and self-serve, finding new things. So when Gen AI kind of became a thing and customer support was trying to implement more Gen AI in the Airbnb support agent, they relied on Chronon pretty heavily because what they found was that effectiveness in customer support really relied on super real-time, fresh context engineering being provided to the agent at inference time. So they found that this worked really well to meet that need. And then also non-AI and ML use cases started coming along, like metrics and even these kind of user-facing metrics. So, if you ever go to a listing and you see the average reviews, like the average number of stars based on the reviews for this listing, that got built on Chronon because it's a real-time aggregation, and writing those pipelines is simply hard if you don't have the right framework for it. So Chronon was the easiest, most compute efficient, and most serving time efficient way to do this. So it was really exciting to see this kind of momentum within Airbnb. And that's when we started thinking about open sourcing. But we really wanted to work with one other big company first to make sure that the API is kind of generalized and that the abstractions were correct and that it worked at scale and it could plug into other infrastructure and that it would be a successful open source project. So before we actually went properly open source, we started chatting with our friends at Strike. And they had the exact same set of goals and challenges and requirements. So we started kind of this closed beta partnership with them. And that, after a couple of months, we were in production with them. And then a couple of months after that, 100% of Stripe's payment traffic is actually powered by Chronon. So every transaction from a UI like this across the internet that processes a payment behind the scenes, Stripe is running fraud detection in their charge path, and all of those models are built and powered using Chronon. Um, Once that happened, we felt pretty good about the open source, about the APIs and the abstractions and the generalizations and the engine. So that's where last year we officially made the project open source. And there's been a ton of really exciting momentum in the community since then. So those of you who saw the Sora 2 launch from OpenAI a couple weeks ago, this is powered by Chronon. So the personalization of the feed. So like, what videos and what things you see, that personalization model, the feature engineering for that, both for training and for inference, is powered by Chronon, as well as these metrics, which again is kind of similar to the Airbnb use case for showing average reviews. Both are powered by Chronon. Uber Eats came along, which has a personalization use case, again, similar recommendations kind of use case. Netflix as well, and a bunch more have been kind of coming on. So it's been a very exciting 12 months in the project. And we've been working with a lot of folks to kind of make sure that it's a successful deployment. So yeah, do feel free to drop into the Slack channel if you have any questions or want to hear more from those guys. It's been a fun community to be a part of. So the scope of Chronon, again, I think a lot of folks in this audience are probably fairly familiar already, so I won't spend a lot of time on it. But basically, at a high level, it takes data in from any raw data source within your company. So it could be batch data in warehouse, streaming data, CDC from bin logs or things like that, as well as external sources. So like external APIs, internal services, or third-party APIs, and then Chronon handles the transformation. So it could be feature engineering, embeddings, things like that, and then downstream it can power model training, model inference, rules, agents. Again, I'm not going to spend too much time on this. I imagine most folks kind of already understand the bounds of a system like this. So with that, let's jump in a bit to recommender systems. So at a very high level, the goal of any recommender system is to recommend items to users. It could be content like Pinterest and TikTok, or it could be items or listings like Airbnb and Amazon. And really, our goal with recommender systems is to improve some metric like a click-through rate or a purchase. And generative modeling has been a really interesting sort of major development in this space in the last year. And I think kind of one of the seminal papers that got a lot of attention and put it kind of on the map in a big way was this HSTU paper from Meta last year that showed a massive improvement in engagement for their content by using generative approaches. So why do they work better? And actually, it's interesting. I think the Coinbase talk actually touched on this. They understand the temporal nature of events better. So, a user that clicked on gardening-related items 3 times in their lifetime versus 3 times in the past 5 minutes after engaging with View Furniture, right? I mean, a model that simply understands the former might be able to say this user is loosely interested in gardening, whereas the latter will form a far richer view of that user, where it's like, okay, they probably, moved homes recently, furnished a new place, and now they're thinking about a landscaping project. So it forms a far more intelligent kind of view of the user and can make better recommendations based off of that. And the mechanism by which it does so is similar to Gen AI LLMs. Instead of having attention on prior words to predict the next one, it's a sequence of user activities and attending over those as tokens to make predictions. Oh, by the way, I meant to say this earlier. I think Nikhil and Piyush, I think a few folks are in the chat who can answer questions for me kind of live real time. So do feel free to drop lots of questions in chat, and they'll kind of try to help. But okay, so the main requirement here for this to work well is long sequences. I think that's been shown to be super important at a lot of use cases, plus real-time events, right? You want to be able to capture that, this user, for example, maybe on average has a lot of DIY content, and then now they're kind of recently engaged in gardening. That together can be used to sort of promote DIY gardening related content. So it's those two things have been really important, and that has major implications on infrastructure. So what are some of the challenges? The first one that I want to talk about, but I think is really interesting, is this challenges that come along with model chaining. So in these systems, and this is a very simplified high-level view, you have 2 models that come into play. So user actions get fed into a sequence model to produce user embeddings, and then that gets combined with other features, item features, as well as many other embeddings, like item embeddings and things like that, to power a second recommendation model. So at a high level, when you have these models being chained one to the other, it produces some like a new set of ML infra, ML ops kind of challenges. And one big one here is kind of our old friend, online offline consistency and leakage. But it takes a new form when you have these model chainings. So to kind of illustrate this, let's say that you have these user activities here, ranging from 90 days ago all the way up to today, and that's used to create embeddings, which becomes training data for model 2, which is, in our case, that recommendation model, but it could be anything. And then, there's other data that gets passed into that training as well. But in that embedding step, if you use that whole range of data, from 90 days ago to today to train a model, and then even if you're very careful to only pass in point-in-time correct sequences for embeddings generation, you still are very likely to run into a leakage situation. And the reason why is that the model itself was trained on that future data, right? And so even if you only pass in this click event, as soon as you run that embeddings inference, if that embeddings model was trained on future data, it will have remembered that that click was followed by a buy, and it'll put that buy intent directly on that click event, which is essentially leaking that future-looking user intent in the embeddings generation that's passed to Model 2 training. So it's not sufficient actually to be very point-in-time correct purely in the sequences that we pass in to the embeddings model. We actually have to be point-in-time correct in the model itself. So what that looks like is something like this, where you use a time range 1 to train a model at time t1, and then you use model t1 to run inference on time range 2, right? And then time range 2 similarly is used to produce training data for model t2, and then that model is used to run inference on model t3. To run inference on data from t3 for batch inference to generate model 2's training data. So basically what this comes down to is you're treating the model itself as time partitioned to ensure that data is not leaked via embedding information. And yeah, I mean, having read a lot of the papers kind of in the space, I think basically a lot of teams are not doing this and bumping into one or two problems. Either essentially this leakage problem that we talked about, or back to like log and wait, which is a very interesting kind of corollary to see in the industry for like the old challenges faced by feature engineering, where like doing some kind of logging of this embedding. So that actually has a lot of other interesting challenges with it, where there's often some accepted inconsistency to reduce the log size and things like that, because logging embeddings is not a very simple thing to do. So this approach of treating the model as time partitioned is kind of our what we think is a pretty unique sort of step forward in supporting these more complex flows. The other big challenge here comes at inference time. So online inference. I kind of had, that previous diagram that I showed, it was very simplified, right? And I think when you look at these recommender systems in production, the actual pipelines that power them are far more complex. So you have, just looking at kind of that top pipeline, you have like item features in batch and streaming that get used to produce essentially an embedding that then writes to the vector database. And then in the search service, you have that whole user intent pipeline that I was talking about previously that needs to run in real time, right? So as the user is kind of taking actions, there's real time updates of user embeddings. And then those are used, as part of the request to get relevant items from the vector database, and to kind of produce that request, which then comes back. And then there's a third kind of fragment of this model, which is that recommender part that actually takes those two things and combines them and produces these items. And so at a high level, sort of the infrastructure challenges that you have here is just a lot of chaining between batch pipelines, real-time pipelines, model inference, indexing, serving, and kind of doing those things in a modular composable way is very difficult. But that's essentially the main extension that we've made to the Chronon API recently, is to support those things. So you don't even need to necessarily have such a complex use case, but what you do have is the building blocks within Chronon to kind of take batch transformation, streaming transformation, model inference, and combine that any way that you want, and then rely on the scalable engine to orchestrate those flows for you, both for training and for production inference. And that's where this has kind of helped teams quite a bit accelerate their development and iteration and deployment of these systems. So kind of to summarize that, what you have here is the Chronon's native Lambda architecture, which offers a scalable engine for batch compute and streaming compute with consistent training data between the two. And then now, the more recent addition is this native API for model chaining, which lets you take those things, produce embeddings, serve those embeddings, and combine them with other features, and run these complex pipelines of recommender systems without needing to worry about that entire orchestration and compute layer, all on your own. Another major point here is that, it's not like we're reinventing the world here on model inference and model hosting. It's very plug and play. So we focus more on the compute of the features plus integrating with existing model systems via our API, and focusing on the orchestration of those data flows as opposed to, um, needing to replace or rip out anything on your model side. So your model platform can stay the same. The API is just where it plugs in, and then the orchestrator can handle the data flows. Yeah, okay, I think I'm right on time. So I'm not sure, yeah, what questions
Great.
come.
Thanks a million, Ver. Um, this is the first time I've seen this particular problem. So the partition time model. So that was extremely interesting to hear about it. And I'm familiar, of course, with sequence features, and I guess you concentrate quite a lot on sequence features like the items. Have you looked at multi-domain, twin tower recommender systems where you have items, and then it's not just predicting the next item, but maybe you're grounding in a different domain some action. Is that something you've been looking at as well? They're quite popular, obviously, for recommender systems.
Yeah. I mean, that's sort of, I try not to get super deep into like two tower architecture here, but that kind of is what this architecture was sort of illustrating. I mean, basically what down to is like this, this recommendation model here is really sort of three models or three model fragments essentially, right? And so what those break down to is like the user tower, the item tower, and the kind of recommendation piece that finalizes the predictions based on those two things. Um, so I think, yeah, I focused a lot on the user sequences here, but really there is a lot of stuff going on, additionally as part of that architecture, right? There's a lot of item features, item embeddings, all of those things getting passed in and generated in these batch and streaming pipelines. Yeah, a bunch of interesting papers and approaches on this. There's actually a really good one from Pinterest recently. I think they're giving a talk here as well.
They go to talk earlier, yeah. Yeah, I guess another question is, if we look at some of the trends in recommender systems, you may have seen that Netflix had their own attention transformer based recommendation system they talked about. Do you see it moving in that direction where, well, attention is all you need, and transformers are the hammer that will solve every prediction problem?
That's a great question, Jim. Honestly, oh man, I don't feel like I'm probably the best person to answer that. I think I haven't done. I mean, I've read a lot of these papers, but I haven't been super deep in the research side of this myself. I've been thinking about it like a lot more from the infrastructure requirements to power it, and that's where kind of like we think about these very pluggable modular primitives. Where what I do think is important is more of this chaining, right? Where like regardless of whether you're applying an attention mechanism or something else, I think being able to take features, take sequences, produce embeddings, and then chain those things arbitrarily and flexibly, and not have to rebuild a bunch of like infrastructure to orchestrate those flows every single time. I think that's what I feel safe banking on. But as far as where the research goes and what shows like what the next step forward is here, I don't know. It's exciting. Things are changing rapidly. Um, I mean, that's it, right? It could like even for like language models, right? Who knows? Who knows what's next?
Yeah, I mean, it's
Um,
out there. But like on the infra side of things, then if you're focusing heavily on sequence models and so on, it would seem that this I talked at the beginning of the conference about convergence and consolidation in the space. It might make. Are you able to divulge some of the roadmap? Are you guys going to be doing serving as well? I guess will be part of the product
yeah,
roadmap and things like that.
Yeah, so this development is happening right now in open source with kind of a collaboration between us, like Airbnb, Netflix, OpenAI. So like there's a lot of there's like a fairly like there's a lot of good discussion here as to where that roadmap is going. We should put some of that out there public facing in the Chronon channel. I think that would be helpful. We haven't done a ton of that yet. But you talk about inference. I mean, definitely, hosting model inference, like I said, I think that'll always remain an abstraction that we are happy to let someone else handle. But I think the vector DB indexing, the embedding indexing and embedding serving, for sure is kind of coming into the abstraction. But again, it's plug and play with your existing storage the same way that our KV store is, right? So we don't have an opinion on what your storage needs to be. We have an API for KV store, and similarly now we kind of have an API for vector store and configuration for how you want to plug that into your pipelines. So like asynchronous user activities, triggering model inference, and the output of that writing to KV store and then being available via this index. That level of configuration is kind of what we're bringing into the API. But the specifics of your storage can always remain implementable by whoever's using the platform. That's kind of at a high level, that's the way we're thinking about it. As far as the exact roadmap and everything, I do think we should get some stuff out there on the channel.
We're excited to see how it goes, and good luck with the next year, Varant.
Thank you so much. Yeah,
Thanks.